Hello everyone. Today I would like to introduce our new work, Plasma. In this new work, we have proposed a novel solution to fine-grain the elasticity management for stateful cloud applications. As we all know, elasticity is a very important feature for cloud applications. With elasticity, cloud applications can change their scale during runtime. For example, initially you only have few requests. Then you only run your applications on a single server. Later, you have more requests coming. Then you scale up your applications and run it on multiple servers. Of course, when the workload decrease, you can scale in your applications to avoid resource over provisioning. There are already many popular elasticity management servers on cloud. For example, on AWS, you have Lambda functions, and also you have auto scaling. And in Microsoft, you have Azure durable function and Azure function. And also you have the Olins. Olins is an actor-based programming language. So let's first talk about the AWS Lambda function. With programmers only need to upload his source code to this AWS Lambda function service. And when a request is coming, the platform will trigger one functions to process their requests. When more requests coming, the platform will trigger more functions to process their requests. So then the platform will take care of the elasticity of your applications automatically. Lambda function works very well with the stateless applications. However, it cannot work with stateful applications directly because each function is executes independently. They can't exchange data, which is required in many stateful applications. Here you can add external storage, and then the functions can exchange data via storage. However, the external storage will introduce long trivial latencies here. Except Lambda functions, programmers can also implement applications with some actor-based programming language. In actor-based applications, actors are distributed across multiple servers. When some requests come in, those actors will coordinate with each other to process these requests. Actor model become quite popular in recent cloud community because there are many important features in actor model. First, it's scalable because actors will exchange communicate with each other through the asynchronous messaging. Also, in many cases, actor-based applications has the low latency because the states of applications are stored in each actor, which is in memory. So there are many works here, like Olins, which is from Microsoft, and Event Wave, and Aeon. But how about the elasticity here in those actor programming language? All of those language, or most of this language, the runtime have provide some kind of the elasticity management, but those elasticity management are quite limited. For example, in Olins, it only place the same number of vectors on each server to achieve the workload balance. Then let's look at a simple example here, PageRank. So usually we will split a large graph into multiple partitions here and place those partitions on multiple servers to conduct distributed graph computation. However, it's very hard to conduct exact balanced graph partitions. For example, in this figure, we have placed the same number of partitions on each server, but the above server is overloaded. So for the elasticity management, we just migrate a smaller partitions from the above server to a bottom server. But then the bottom server is overloaded. So we have to add an external server and migrate one partitions here, there. Then we have get the required performance. Obviously, this Lambda function cannot works very well for the in this case because partitions are stateful, and if we use external storage, it will introduce long trivial latency here. And also, all this elastic management cannot work here because he just simply put the same number of partitions on each server, which already show that it doesn't work. So then we found if you want to have the fine-grained elasticity management for the stateful applications, you need more information. For example, you should understand what the applications it is, what's the logic of the applications. Also, you need the user requirements. Some users more care about performance, but others more care about their cost. Then server runtime information also important because you should know which server are overloaded. And application runtime information is also required because you should know which component or which object is a bottleneck in these applications. So we have designed and implement the elastic programming framework called Plasma. In the Plasma, we have the Plasma language allow programmers to define their elastic management, and the Plasma runtime will keep connecting the server runtime information and application runtime information, and based on the input from the users, they will conduct automatic elastic management for stateful applications. We have implemented Plasma on the AYAN actor programming language. So to use Plasma, programmers only need to implement an AYAN program as usual. So and here they only need to focus on the logic of their program. And then they need to implement a separate Plasma program to define the required elasticity management. Then the compiler will generate a executable file and the configuration file, and deploy on the clusters, and then the runtime of the Plasma will conduct elastic management for your application automatically. At first, let's look at the programming language. Plasma program consists of multiple elastic rules. For example, this is the elastic rule for PageRank. So a single elastic rule includes two parts: conditions and behaviors. It means some particular elasticity behaviors will be triggered when the conditions are satisfied. These conditions you can refer server runtime, actor runtime, and semantics. So here we have referred the server runtime information. This rule means that when the server CPU usage is larger than 18% or smaller than 16%, some behaviors will be triggered. So here we have the balanced elastic behavior. It means it will balance the workload for the CPU resources, which will migrate actor from overloaded server to idle servers. Now we have 5 different behaviors in our prototype, except balance we also have collocate, which will collocate 2 actors on the same server. Elasticity management runtime includes 2 parts: profiling runtime and execution runtime. Profiling runtime will keep connecting runtime information of vectors and servers. The execution runtime includes local elastic manager on each server and multiple global elasticity manager. The elasticity management will be triggered periodically. When the management is triggered, the local manager will read the runtime information from the profiling runtime and will process some elastic rules only need local information. For example, to collocate 2 actors with frequent interaction. But for some other rules, like which need global information, like to balance the workload, the local elastic manager will randomly pick up a global manager and send those runtime information to that global manager. So after global manager connecting runtime information from local manager, he will decide how to migrate the actors. But here, global manager will not migrate actors by themselves. He just make decision and send this decision back to the corresponding local manager. The local manager will conduct the actual migration. So we have implemented our Plasma programs for more than 10 applications, and we use 5 of them to evaluate our Plasma. Here, I would like to show one experiment, PageRank. We have choose one graph from a popular graph repository set, and we use Matisse to split this graph into 32 partitions. In the first experiment, we fixed the resources to 8 servers, with each server have 2 CPUs. Initially we place the 4 partitions on each server, and we compare Plasma with Mizan, which is an elastic graph computation platform, and Orlin's elastic management, which will put the same number of partitions on each server. So clearly, this figure shows that Plasma has improved the performance by 24% with the same number of CPUs. Next, we want to show that with Plasma, you can achieve the similar performance with much fewer resources. So in the comparison setup, we just place the 32 partitions on 6 servers. Each server have 2 vCPUs and take 2 partitions. In this way, CPU will not be a bottleneck. And in Plasma, we place all the 32 partitions on a single server. And then the Plasma will conduct elastic management. So after a while, you can see that the Plasma have achieved a similar number with the over-provisioning cases. But in this case, we only use 12 servers, which have saved 25% resources here. So okay, this is I just introduced our work Plasma briefly. If you need more details, you can read our paper or just visit our project website, which is also included in our paper. Thanks.